Okay, welcome to another video. Now we're going to talk about the Big M method. So up to this point, we've dealt with maximization problems that only have less than or equal to constraints. And we've always made sure that the right-hand sides are always non-negative, and actually they've always been positive. And when that's the case, we have an obvious choice for our initial basic feasible solution, which is just use all the slack variables as well as z in our basis. Okay. However, there's a lot of situation where this isn't going to work, because that assumes sort of that if I set all my original variables to 0, that it gives me a feasible solution. Okay. Which when we have less than or equal to constraints, that's usually true then. But if we have greater than or equal to constraints or equality constraints, it's usually not true. So usually setting all our original variables to 0 is not going to give us a feasible solution when we have greater than constraints or equality constraints. So today we're going to address these two questions. If my linear program is feasible, how can I find an initial basic feasible solution? Once I've found one, I can follow the simplex method through to find the optimal solution as long as I can find one. Okay. The other question that we'll consider is, if my LP is infeasible, how can I know? It's perfectly possible that there might be no feasible solutions, and you need to know when that happens. Often this is because you've over-constrained your problem. You've added too many constraints, and it's not possible to satisfy all those constraints. Okay. So the big idea behind the Big M method is that we're going to do something called relaxation, and that we are going to relax any violated constraints. And this is just a fancy way of saying we're going to add more wiggle room to them. And we're going to do that by introducing extra variables. And we're going to call these variables artificial variables. The artificial variables act a lot like the slack variables, but unlike the slack variables, which sort of told us how much slack is in our constraint, they're going to tell us how much we violate our constraint. Okay, and we're going to introduce these in a way that allow us to violate the constraint, but we do so at a penalty to the objective. So it's sort of like, I'll let you cross over the line of the constraint and go on the wrong side of the constraint. But for every unit you cross that line, your objective is going to go in the wrong direction. Okay. And so that's the big idea behind the Big M method, is that we'll relax those constraints. We're going to introduce these artificial variables, but we do so at a penalty to the objective. So let's say we've got a problem where we want to maximize z equals 3x1 plus 2x2. Okay. And let's say we have just one constraint, and our constraint is 2x1 plus 5x2 equals 7. Okay, let's say we have an equality constraint, and let's say that's the whole linear program, that we just want to maximize this subject to this, and then maybe as well the non-negativity constraints. Okay, so the idea is that we're going to, this is already an equality constraint, so it doesn't need any slack. It doesn't want any slack, right? The inequality constraints, there is no slack. This side must be equal to this side. Okay, but what we can do is we can introduce an artificial variable. And that artificial variable allows us to violate this constraint. It allows us to choose x1 and x2 such that 2x1 plus 5x2 does not equal 7, but we're going to impose a penalty to the objective for doing that. And so here's what we're going to do. We're going to do 2x1 plus 5x2, and then we're going to add an artificial variable. And I'm going to use the same s for my artificial variable, but I'm going to put a bar on top of it. Okay, and that's just going to be how I'm going to denote that this one's an artificial variable as opposed to a slack variable or surplus variable. Equals 7. Okay, and so if we kind of were to rearrange this and think about and solving for S1, S1 is 7 minus 2x1 minus 5x2. It's the difference from ideally S1 bar is equal to 0, but it's essentially measuring how far away we are from that constraint boundary. Okay, and for an equality constraint, we can't go anywhere on either side of it. And so yeah, this will sort of penalize us. So then what we want to do is we want to impose a penalty on the objective. And so our new objective becomes maximize z equals 3x1 plus 2x2. And then because we want to maximize this, we're going to put a negative penalty. And so for as large as S1 is, we're going to try to impose a penalty that's negative, and we'll put big M times S1. So if S1 is any positive quantity, it's going to make this term very large and negative, which is going to work against maximizing that Z there. Okay, and so ideally, we're going to drive S1 bar to 0. It can't go negative because we'll put, I guess maybe I should note, S1 bar is going to be greater than or equal to 0. It's going to have a non-negativity constraint as well. But if it's any positive amount, then that's going to put a big negative on our objective and reduce our objective value. Okay, and so we create this new optimization problem that has a slightly larger feasible region. Okay, because we've essentially introduced this S1 bar that allows what previously were infeasible solutions are now feasible for this new problem. But this new problem is going to work really hard to try to drive S1 to 0. What's M? M is any big positive number, right? And we're subtracting it. So it can be a big positive number. And as long as it's big enough, it will drive S1 to try to be 0. Okay. When we work these ones by hand, we'll just leave M in as a big number. And the main thing to note is that M is bigger than any other number in the problem. And so it sort of wins when we're trying to do any sort of test of what we should, of comparing numbers. Okay. So let's do an example. And so we've got this example. We finally got a minimization problem. Okay, we've only dealt with maximization problems in our example so far. We've got 2 of these greater than constraints, an equality constraint. Let's go ahead and draw a picture of this. So if I draw a picture of this, we'll label that X1 and this X2. I could do this in Desmos would be a good way to do it. But let's see this first constraint here. Yeah, I'll go ahead and I'll draw this in rather than you watching me think through this. And so I'm going to pause the recording for a second. Okay, I used Desmos to help me a little bit. This is what the feasible region it looks like. So this first constraint is this A constraint. It's a greater than or equal to. Oh no, let me see. Oh, I mislabeled the constraints. Never mind. This one is B. This one is A. Okay. There. Yeah, that's better. Okay. So this one's a greater than or equal to, but it's you can kind of multiply this through by a negative, and I'll do that in a second. It actually flips it around. And so that's the first constraint. Here's the second constraint, greater than that. Those two combined give this region as the feasible region. And then this equality constraint says it has to be along this line for C. And so the only thing that satisfies all 3 of those is this portion of the line from here to here. Okay, so kind of your feasible regions get a little bit complicated when you throw equality constraints into there. But that's our picture for it. Okay, let's work on how would we set this up. Okay, so a couple things as we set it up. We will be minimizing z equals, and then I'm going to kind of line things up and work on these one by one. First things first, let's, well, I guess we're going to have 2x1 plus 3x2. Now let's look at this first constraint A. And in this constraint A, I've got a negative on the right-hand side. And we've said that we use checking whether the right-hand side is positive or negative as sort of a way to check for feasibility. And so we want to set it up so we always have a positive right-hand side. So I'm going to multiply this equation through by -1. And when you have an inequality and you multiply by a negative, it flips the sign of that inequality. And so this constraint A, once we multiply through by negative, becomes 0.5 x1 plus 0.25 x2 is, we flip the inequality is less than or equal to 4. So I multiplied that through all by -1. And so then copying that down here, 0.5 x1 plus 0.25 x2. I'm going to leave quite a bit of space. Let's see, maybe all the way over to here, equals 4. And we're going to put this in augmented format. And so we've got a less than here. So we're going to introduce a slack variable. And so I'm going to call this plus, well, let's keep our equations labeled A, B, C there. And so I'll call that slack for constraint A. Okay, that's the first one. And that was a less than or equal to constraint. Don't need any artificial variables if you got less than or equal to constraints with a positive right-hand side. Okay, if you got a less than or equal to constraint with a negative right-hand side, multiply through by a negative, and it will become a greater than or equal to constraint with a positive right-hand side. Okay, so maybe step one is make sure all your right-hand sides are positive. If you need to, multiply by a negative. Okay, now let's look at B. So that's going to be 1x1 plus 3x2. And then we've got a greater than or equal to 20. So I said earlier, if we want to change a greater than or equal to into a equal to, so turn it in augmented form, we need to subtract a slack variable. Okay, and so we'll call this, or subtract a surplus variable. So we're going to subtract SB. Now, if I were to set x1 and x2 equals 0, then I'd be left with SB is negative SB is equal to 20, or SB is equal to -20. But our surplus variable has to be greater than or equal to 0. We'll still have our non-negativity constraints. And so that would violate feasibility right from the beginning. Okay, so to account for that, when we have a greater than or equal to constraint, we also then add in an artificial variable. And I'll give it the same subscript, but I'll give it the bar over top of it to denote that it's an artificial variable. Okay. Third constraint is going to be x1 plus x2 equals 10. Now that is already sort of in augmented form. We've already got an equality. We don't have an inequality. But if I plug in 0 for x1 and a x2, I get 0 equals 10, which is a false statement. So I need something to sort of take up sort of the slack that's there, even though no slack is allowed. And so I'm going to introduce an artificial variable here plus SC bar. Okay, and this is going to be my constraints in my new augmented formula with artificial variables. Now, anytime I introduce a artificial variable, I've got to penalize my objective. And so this, I want to drive this to 0. And so I'm going to add a minus big, I'm going to put a MSB bar there. Now let's think about what sign should be in front of this. I'm now doing a minimization problem. So what would work against minimization while making something big? And so actually in this case, instead of subtracting, I'm going to add. Okay, and so always choose this sign depending on what penalizes your objective. So if you're trying to minimize, add a penalty. If you're trying to maximize, subtract a penalty. And I'll do the same thing for my other artificial variable, SC bar. Okay, maybe to kind of summarize things here, I'll make you a little key. So if you've got a let's see, a less than or equal to constraint with a number here, I'll maybe just put a positive number in, knowing that you need to always have a positive number on the right-hand side. So if you got a less than or equal to a positive number, that ends up being plus a slack variable, and then equal to that number. If you've got a greater than or equal to some number, like 4, then you're going to introduce both a surplus variable, so you're going to subtract that, and you're going to add an artificial variable as well. Okay, I tend to give them the same index, and I give them the index that matches whatever constraint I'm talking about. And then if you're given an equality constraint, then you just add the artificial variable. And then also penalize the objective. So if you got a maximization problem, z equals ... we're going to subtract big M times our artificial variable. If you've got a minimization problem, we're going to add our penalty. And if you have multiple artificial variables, you do this for all of your artificial variables. Okay. It will make a little bit sense as we sort of work through a problem here, or work through this problem. Let's go ahead and put this into our Tableau. We're going to leave these M's as sort of arbitrary big numbers. We're not going to give them a value yet. When we work in R, we'll have to give them a value though. Okay, let's translate this into a Tableau. I'll start a new sheet of paper here so that we can kind of work through the Tableau method here. And so columns are going to be Z. I'm going to need a column for my X1 variable, X2 variable, slack for the A constraint, surplus for the B constraint, artificial variable for the B constraint, and artificial variable for the C constraint, and then right-hand side. Okay, so yeah, when you start getting these artificial variables, you end up with a lot of extra variables by the end. Okay, so my objective is going to be, once I move everything to the other side, that's maybe a good point to make, is I need to move everything to the other side, and so I'm essentially going to subtract them all. So actually, maybe I'm going to kind of cross out that equals there, subtract this, subtract this, subtract this, subtract this, and then we're equal to 0 here. Okay, so putting that in here, I've got 1z minus 2x1 minus 3x2. The slack variable doesn't show up. The surplus variable doesn't show up. The artificial variable is going to get a minus big M, and the other artificial variable will also get a minus big M, and my right-hand side is going to be equal to 0. And that's my objective row. So, and then let me go ahead and copy down my constraints. So let's see. 0.5, 0.25, 1, 0, 0, 0, 4. It's going to have a 0 there. 0 here, 0 here. 1, 3, 0, minus 1 for SB, plus 1 for SB bar, the artificial variable, 0 and 20. And then 1, 1, 0, 0, 0, 1, and 10. Okay. Let's label our rows with our basis. What do you think would make a good basis? Well, Z is always going to be in the basis. Z, the first row is always going to correspond to Z. SA has that second standard basis vector already in it. And so that's going to be the second row. Looking here, SB almost looks like it, but notice it's got a negative here. And if I were to sort of get rid of that negative, it'd mean multiplying this row through by negative, and then that would turn our right-hand side negative, and we don't want that. So instead, I'm going to actually choose the artificial variable SB bar, and for the last one, SC bar as my third basis. Okay, so the rule of thumb for your initial basis is that you choose slack variables for less than or equal to constraints and artificial variables for greater than or equal to constraints. Okay, or equality constraints as well. Okay, so that's my initial basis, but notice it's not quite ready. Okay, meaning that looking at the column for this basis vector, it's not exactly this the standard basis vector because we've got this minus m up here. And same thing here is I'd want this to be 0, 0, 0, 1, but it's got this minus m up here. And so we have to do kind of a half setup iteration where we need to do a row operation that's going to zero out these values here. Okay. And so we're going to use this row, and we're going to add a multiple of it up to here that's going to cancel this out. And so I'm going to kind of do just kind of those operations and record the result down here. And so let's see, we're going to do big M times this row, big M times 1 plus negative big M is going to get me 0, which is what I want here. So I'm going to take this row, add M times that row and add it up. And that's going to give me the result of, so I'm going to take this row, add big M times it up. I'm going to have a 1 here. I'm going to have a big M minus 2. 3 times big M minus 3, so 3M minus 3. 0 times big M plus 0 is 0. Negative 1 times big M plus 0 is negative big M. Big M times 1 plus negative big M, that zeroes that out, which is what we wanted. And 0 times M plus negative M leaves us a negative M there. And 20 times big M is going to give us 20M here. Okay, so here's sort of, I guess this is sort of our, we're gonna do this at work in progress. And so in this case, this is still our 0. We're not quite done with it yet. Okay, and so we got a 0 up to here, and so we can kind of think of crossing this row out now, and this is our new top row. Okay, so we got a 0 here, and we wanted a 0 there. We also want a 0 here, and so let's go take, and to zero that out, we're going to take big M times this here and add it down to cancel that out. And so we're going to do big M times that row and add it down, and we'll get another version of that same 0 objective row. So big M times this row gives us 0 plus 1. The Z still is going to be a 1 there. A 1 times M plus M minus 2 is going to give us 2 big M's minus 2. M times 1 plus 3M minus 3 is going to give us 4M minus 3. Big M times 0 plus 0 is 0. Big M times 0 plus negative M is negative M. Big M times 0 plus 0 is 0. Big M times 1 plus negative M, that zeroes that out, which is what we wanted. And then 10 times M plus 20M is going to give us 30M. Okay, and then that will replace this row there. Okay. The rest of the matrix corresponding to the constraint parts doesn't change. I'll copy it down just for clarity. And so I'll copy that down. feel free to pause the video and catch up. I'll pause the recording. Okay, if you need to pause the video, you can. Here's our new starting tableau. Okay, we essentially modified this top row to get zeros here and here because there originally were negative big M's there. The result is that we got some big M's other places in the top row. And maybe the thing to be aware of is this is a minimization problem, so we want to make this as small as possible. But now our starting objective value is 30 times a big number. So if M is 1 million, we're maybe starting off at 30 million, and now we're trying to bring it down, okay? So we're, yeah, in a minimization problem with big M, you start off at an astronomically big value, and you try to get closer and closer to the feasible region in order to reduce that penalty. Okay, so we're trying to reduce our penalty to get to our feasible region. Okay, so this is also our first minimization problem, so we should talk through kind of the changes that are there. But before we get into that, what is our current solution? Well, our basis variables are still SA, SB bar, and SC bar. And so our solution at this step is Z equals 30M. So it's huge starting value for our objective that we're trying to minimize. SA, we've got that equal to 4. So we got 4 units of slack in the first constraint. That's fine. Our artificial B variable is 20, which means we're violating our second constraint by 20 units. And our artificial C variable equals 10 because we're violating that constraint by 10 units as well. Our other variables of x1, x2, S and SB are all equal to 0. And so we got 3 non-basic variables, which are x1, x2, and SB, which is the surplus for the second constraint. There's no surplus now. There's this SB is essentially the anti-surplus, the amount that we're short on that greater than or equal to constraint. Okay, so that's our current solution. Now, the difference when we're doing a minimization problem is when we scan this objective row, we don't want to look for negatives, but rather we want to look for positives, because the positives, once we move them over to the other side of the equation, are what's actually going to reduce our objective. Okay, so we want to go the opposite direction because this is a minimization problem. So looking at our objective row, we've got 2m minus 2. Now, m is a big number, so 2m is much bigger than the minus 2 here. So this is positive. We've got 4m minus 3. 4m is much bigger than minus 3. And then we got this minus m. So we don't want to pivot on this. This would actually move us in the wrong direction. But we want to pivot on either x1 or x2. Either one of them has a positive value in the objective row. I'll follow the rule of thumb of choosing the larger of them. And so I'm going to choose the one with 4 m's rather than 2 m's. Okay. And so I'm going to choose this as my entering variable. And that's the column that corresponds to x2. And then now I need to do my ratio test. And so 4 divided by a quarter is 16. 20 divided by 3 is, well, 20/3. And 10 divided by 1 is 10. Okay, so 20/3 is smaller than 10. And so that's going to be our pivot row. So let's go ahead and circle this one. Ooh, this is not going to be the nicest algebraically, but I think looking ahead, it doesn't get too bad. Okay. Oh shoot, I forgot to do a trick. Okay, so never mind. It'll be fine. It'll be fine. I was just realizing in my notes that I had done a little trick to get rid of the fractions in this one by essentially multiplying that row by 4 to clear the fractions, but we'll ignore that. Okay, so we're going to do this row. Let's go ahead and yeah, do that pivot. So I'm going to keep things sort of lined up and do my do everything right below where it was last time and just kind of line things up here. So I've got a 3 right here in my pivot spot, pivot column, pivot row. I want to turn that into a 1. And so I want to multiply this whole row by 1/3. And so that middle row is going to go 0, 1 times a third is 1/3, 3 times a third is 1, 0, negative 1/3, 1/3, 0, and 20/3. Okay. And now I want to go ahead and get zeros here, here, and here. Okay. Filling in the things that I know won't change is I know that this one will stay a standard basis vector. I know this will stay a standard basis vector. And I know that this will stay a standard basis vector. Okay. Makes my life a little bit easy as far as what's going to fill in or not. Okay. Let's go ahead and try to get our 0. Oh, let's see. Yeah, 0 up here. We're going to take, we've got 1 here. We want to get rid of 4m minus 3. And so the trick is when adding up there, we're going to multiply by negative 4m plus 3. Okay. Let's see if we can do it. It's going to be a lot easier once we do this in R. But so negative 4m plus 3 times 1/3 is going to be negative 4/3 m plus the positive 2m, negative 4/3. Okay. Negative 4/3 plus 2m is going to leave us with 2/3 m. 1/3 times 3 is 1, plus the minus 2 is going to give us minus 1. Okay. Over here, negative 1/3 times 4m is going to give us 4/3 m, and we got a negative m there, is going to give us 1/3 m, and then minus 1. And then multiplying this with that is going to give us negative 4/3 m plus 1. Okay. Multiply this by negative 4m plus 3, and we'll get negative 80/3 m. And so negative 80/3 30 m plus 30m. 30m is 90/3 m. And so that's going to leave us with 10/3 m. And multiplying that, it's going to give us plus 20. Cool. So I'm going to fill in the rest of the row operations, or at least I'll tell you what I'm going to do. Then I'm going to pause so you don't actually have to watch me kind of struggle through, and you can feel free to try it yourself and then unpause and see if you got the same thing for me as I did. We're going to want to cancel this quarter out. And so we're going to want to take this row, multiply by negative 1/4, and then add it up to here to get a 0 there. We're going to want to cancel out this 1 here. And so we'll do negative 1 times the row and add it down there. Okay. Do those 2 row operations and then check back in with the video. So pause. Okay. Check in. Did you get the same tableau as I did? So double check. These are your answers here. Let's maybe, I kind of wrote these in the way here, but I'll kind of write our row labels on here. Our basic variables are Z for the objective row, and then it's going to be SA here still. Instead of SB bar, our entering variable was X2, and then we still have SC bar here. So our solution at this stage is going to be Z equals 10/3 m plus 20. So still a big number. SA is going to be equal to 7/3 of slack for that constraint. X2 is now 20/3, means we're making 20/3 of whatever X2 is. And then SC bar is equal to 10/3. We're still violating that constraint, but it turns out actually less than before. And then all of our other variables are non-basic, and so they're set to 0, in that X1 is equal to 0, SB is equal to 0, and SB bar is equal to 0. Okay. So let's look at the top row, and we want to look for positive values in the objective row. Okay, so this -4/3 m plus 1, that's going to be negative. 1/3 m minus 1, that's going to be positive. 2/3 m minus 1, that's also going to be positive. So I could choose either of these two rows. I'm going to go ahead and choose this one here. It's got the larger positive one. And so, or larger positive coefficient of m. So I'm going to choose that. Now let's do my ratio tests. 7/3 divided by 5/12 is going to be 28/5. 20/3 divided by 1/3 is 20. And 10/3 divided by 2/3 is 5. Okay. This one's going to be right around 6, and so the smallest one actually ends up being 5 here. Yeah, this is a little bit less than 6, but bigger than 5. And so 5 is the smallest one here. And so our pivot row is going to be this one. And that's actually good because that's one of our artificial variables, and that's going to be our exiting variable. We're going to get rid of our artificial variable from our basis, which is the whole goal of what we're trying to do here. Okay, so I'm going to go ahead and multiply this row by, well, here, pause the video, go ahead and see if you can do the correct pivots. It's a little bit nasty with kind of fractions in here, but it's good practice. If you want to skip over the practice, feel free to just unpause the video, and I'll show you what the final result is from this pivot. Okay, so actually, I'll show you all a little trick that I often use, in that the first kind of pivot, or first part of the pivot that I do, is always up to the top row. And then I look at my top row and I figure out if my top row is optimal, I don't really need the middle of the tableau anymore. And so I save myself some work by kind of doing the top row first. And so looking at this now, I've got a negative here, negative m plus a half, that's going to be negative. Negative m plus 3/2, that's going to be negative. And so at this point, for a minimization problem, I'm done if I've got all zeros and negatives, okay? The opposite of a maximization problem. And so this tells me that this is going to be the optimal tableau, okay? In which case, then I don't need these values in the middle here. I do, though, need the values on the right-hand side here and here. And so just thinking of, I've got a 1 here, I need to get rid of a 1/3 here. And so I'm going to do minus 1/3 and add it up to this row. So if I do minus 1/3 times 5 is negative 5/3, plus 20/3 is going to give me 15/3, and 15/3 is just 5. And then if I want to cancel out this 5/12, I'll multiply by minus 5/12 and add it up. And so 5 times negative 5/12 is going to be negative 25/12. And if I add that to 7/3, 7/3 is 28/12. Minus 25/12 leaves me with 3/12, and 3/12 is 1/4. Wow. This got ugly algebraically. Worse than it was in my notes, because I forgot to use a nice trick at the beginning. So checking the objective row, they're all negatives. So notice that the m's completely canceled out here. The m's also canceled out here, so that I've got 0 m's over here. And this is key. You know that you're at a solution that's feasible in the original problem when there's no longer any penalty m's in the objective value on the right-hand side. Okay, you know that you've gotten to something that is feasible in the original one because you've gotten rid of all the penalty. So our new solution here, and this is going to be our optimal solution, is that this row is the x1 row. Maybe I'll kind of label that as x1. This row was the x2 row. This one was SA, and then Z. And so Z is equal to 25. X1, I'll kind of do them in order here. X1 is 5, X2 is 5, and SA is 1/4. Okay. And then all my other variables are non-basic and set to 0. So SB equals SB bar equals SC bar equals 0. And the important thing is that I've set both of my artificial variables to 0. If I get to an optimal solution where I didn't set my artificial variables to 0, that'd mean there weren't any feasible solutions. Okay, but I'm now feasible in the original problem because my artificial variables are now 0. So that's my solution. Kind of bringing it full circle. The big idea here is relax the constraints, introduce these artificial variables, but add a penalty. The penalty will force the simplex method to try to get rid of those artificial variables first. Okay. Once it's gotten rid of those artificial variables, it might do additional steps. In this case, as soon as we got rid of the artificial variables, we happened to be at the optimal solution. Visually looking at our picture, our first let's see, our first iteration took us from, let's see, 0, 0 for x1 and x2 to after one step, let's see, after one step, x2 was 20/3. And so we started here, we moved up to here, and then we moved along this constraint to right here, and that ended up being the optimal solution right there. So this is kind of our initial spot after one iteration and after 2 full steps. Okay, that's it for this video. The next one will make a slight variation on this example.